Hello everyone, this is C241 Material Science, Serdar Göktepe speaking. In this video lecture, we will cover the first part of the chapter on viscoelasticity. So viscoelasticity is a kind of material behavior that refers to time and rate dependent response of materials. This kind of material behavior may result from the internal non-equilibrium mechanisms of deformation that continue even if you stop loading the material externally due to the dynamical behavior, for example, thermally agitated polymeric chains in polymers. Viscoelastic material behavior might also arise from the presence of a fluid phase in the material. So if you have a porous material, for example, with the pores that are connected, if the fluid phase has the freedom to move through the pores, then this generally naturally results in a rate-dependent response. So examples are in civil engineering, concrete and soil, in biomedical engineering, biological tissue, and in mechanical engineering, a sponge is an example for this. So let's first take a look at some experimental observations based on the experiments on rubbery polymers, elastomers, and then define what we mean by viscosity based on fluid mechanics. So in this slide, what you see is a hyperbolate elastomeric specimen that is subjected to cyclic shear. The deformed shape of the specimen is depicted on the first panel on the top, and the bottom panel we have two plots. One on the right corresponds to the loading deflection curve or displacement curve recorded for a lower rate of deformation, which is 4 millimeters per minute, while the one on the right is the force displacement diagram corresponding to the 10 times faster loading rate, in other words, 40 millimeters per minute. So when you compare these two diagrams, the curves, the first thing that we observe is that higher the loading rate, the stiffer the material response becomes. So in contrast to elasticity, in this case, we have a rate-dependent, loading rate-dependent material response. For the lower loading rate, as you see, the maximum force that is attained in a positive direction is slightly lower than 400 newtons that you see here. Or so in the higher rate of loading, on the other hand, we have this force magnitude higher than 400 newtons. So another interesting observation is that as we increase the loading rate from 4 millimeters per minute to 40 millimeters per minute, we see that the area of the hysteresis, which is an indication of the dissipation, increases as well. So, but this is not a general trend or tendency of the materials that they dissipate more as you deform them faster. Generally, there exists an optimal dissipation is maximum, and this optimum rate of deformation has a relation to the internal time scale of dynamical mechanisms taking place inside the material microstructure. For example, the relaxation times of the polymeric chains. So besides the hysteresis that are also depicted here on the static diagram observed for another kind of polymer, we also observed stress relaxation. So on the diagram to the right, you see that we have a force versus deformation curve, and in this case we have 4 cycles of deformation, and in the actually 3 cycles of deformation. sorry, four cycles of deformation. And in the fourth cycle, somewhere at the strain value about the 40%, we stop the external deformation and observe what happens to the stress. And as you see in this close-up, stress relaxes, in other words, reduces for the constant deformation. If you further load and unload and keep the deformation frozen at the same deformation value on the unloading curve, you also observe some changes in this stress, and you see stress converges to some value, and this value is what we call equilibrium response of the material in polymers, referring to the ground elasticity. So if we had an elastic material, we would not observe such a stress relaxation at a constant deformation when we keep the stress constant, strain is constant, or vice versa for elastic materials, but this is obviously not the case for viscoelastic materials. So these are the experimental observations typically made for viscoelastic materials. Besides the relaxation test or cyclic test or the experiments conducted at different rates of deformation, one can also run experiments at the constant rates of stress or constant stress values. These refer to the phenomena creep that we will discuss in the upcoming slides, also chapters. So let's first define what we mean by viscosity. So that is the first component of the viscoelastic response. So viscoelasticity, as the name implies, is a combination of the viscous response and the elastic response. So that makes the problem rate dependent. What makes problem rate dependent is, in other words, the viscosity. So we have seen in the preceding chapter that the plastic deformation occurs by dislocation motions in crystalline materials, but when we consider the plastic deformations in non-crystalline, in other words, amorphous materials, we typically observe that plastic deformations or viscoplastic deformations are due to the viscous flow, although at different time scales, right? So there's a huge spectrum of time scales for inelastic deformations in amorphous materials. And the characteristic property of the viscous flow is that the viscosity of the material that can be considered as the resistance of an amorphous material to flow or deformation. To visualize this, let's assume that we have a fluid. On top of the fluid that you see with the height or depth denoted by L. L is the vertical dimension. And on top of this fluid, we place the plate denoted by plate A, and assume that we pull this plate with the force towards right, force F towards right, and when we pull this plate, we generate a velocity profile in the fluid. So the velocity is 0 at the bottom of the fluid, and the velocity is equal to that of plate at the interface between the fluid and the plate. And assume that for the fluid we have at hand, this velocity profile is linear. In other words, the gradient of the velocity with respect to the vertical dimension, in other words, the depth is constant. So the rate at which particles change their position is the measure of the rate of the flow. All right, so this is the velocity, and when you take the derivative of the velocity with respect to the depth L, this can be considered as the derivative of the shear strain with respect to time. Why? Because the strain itself, remember, shear strain itself is the derivative of the displacement with respect to height, right, in the two-dimensional setting. So if you change the order of differentiation, you can first take the derivative with respect to L, time, and then take the derivative with respect to the depth dimension to obtain what we call either velocity gradient or rate of the shear strain. So for Newtonian fluids, This velocity profile is linear, and the force that is needed to generate such a velocity profile for a given Newtonian fluid is given by eta times velocity gradient, or the rate of the shear strain, times the cross-sectional area of the plate. In other words, the area of the bottom part of the plate that is in contact with the fluid. So this proportionality constant here, denoted by Greek letter eta, is what we call the coefficient of viscosity. So what you can do is you can divide the both sides of this equation by the cross-sectional area to obtain shear stress, as you recall from the preceding chapters. Then the shear stress can be written as the coefficient of viscosity times the velocity gradient, or equivalently, as we will use it in the upcoming slides, coefficient of viscosity times the rate of the strain, in this case, shear strain. All right, so when you consider this expression, we know that the unit of the stress is force per area, force per length square. And we also know that velocity is meters, a length per time, meters per second, for example, and the length is the length. So the velocity gradient has the unit of 1/seconds. The same thing happens for the rate of the shear strain. Since the strain is non-dimensional, derivative of the strain with respect to time has the unit of 1/second. So when you compare the units of the left-hand side and right-hand side, on the left-hand side, let's say we have a force per length square. On the right-hand side, we have eta, the unit of eta times per second. So the unit of the eta then should be force per length square times second. Typical SI units corresponding to this dimension is the pascals seconds, right? So pascal second is the unit of the coefficient of viscosity. In contrast to elasticity, remember in elasticity we have a stress and a strain, and in between we have a moduli, and moduli have the unit of pascals, right? So in this case, in viscous relationship, we have stress is proportional to the rate of the strain, not the strain, but the rate of the strain. Therefore, the unit of the coefficient of viscosity, that is the proportionality coefficient there, or material property for Newtonian fluids, its unit is not in pascals, but pascal seconds. That is something very important to observe. So here are the viscosities of some liquids taken from the literature, given in millipascal seconds. Okay, this m stands, little m stands for millipascals. If we had capital M, that would mean megapascals, as you know. So water has the 1 millipascal second viscosity at 20 degrees Celsius. So acetone, as you see, is about 1/3 of that of water. Olive oil is more viscous than water. That is that is something we observe also in our daily life. There are also more viscous fluids listed here. So you see, so viscosity changes from one material to another, one fluid to another fluid. These are some representative figures for different example fluids, liquids actually. So we said that for Newtonian fluids, stress is proportional to the rate of the strain through the coefficient of viscosity. So if you draw the shear stress versus rate of the strain, shear strain, we have a linear diagram, right? And this linear curve has the slope of what we call the coefficient of viscosity. But in nature, in practice, there are also fluids that are not Newtonian. We call these fluids non-Newtonian fluids. These fluids can be classified as pseudoplastic or dilatant. So the ones that are denoted by pseudoplastic in this diagram are also referred to as shear thinning materials. The reason is that when you increase the rate of the strain, the slope of this curve gets smaller and smaller. Therefore, we call these kind of materials shear thinning materials. Dilatant non-Newtonian fluids that are denoted here in the lower curve, on the other hand, are the shear thickening materials, because when we increase the rate of the loading, the viscosity, in other words, the slope of the curve gets greater. Therefore, the higher the loading rate, the greater the resistance of this fluid becomes against the flow. So all these three curves can be at least qualitatively expressed mathematically in this formula. If you just go back and rewrite this expression by dividing both parts by eta, right, and put an exponent in to the shear stress tau, we see that when n is equal to 1, the response is Newtonian. When n is greater than 1, the fluid becomes pseudoplastic, in other words, shear thinning. This would mean, again, when you increase the rate of the loading, it becomes easier to flow. When n is n is smaller than 1, then we have dilatant, in other words, shear thickening materials. So non-Newtonian behavior of the fluids generally arise from the structural organization of the fluid molecules due to the flow. For example, in polymer melts or solutions, we have polymer chains in the solutions, and when these chains align in an anisotropic way, in other words, in the direction of the flow, this might result in pseudoplastic behavior, in other words, shear thinning. In the colloid, similar behavior is observed when the particles in the colloids get segregated. All right, so these are basically the mechanisms, example mechanisms responsible for non-Newtonian behavior of the fluids. So we have already defined what we mean by Newtonian fluids and non-Newtonian fluids. Examples for Newtonian fluids are water, air, alcohol, gasoline, tin oil. In other words, tin oil means, as you know, the oil that can flow easily at room temperature. So, of course, everything is here referring to the ambient temperature, which is about 20 degrees Celsius. When we talk about thick oil, like grass oil, then that is as you know, much thicker than much viscous than tin oil, much more viscous than tin oil. So pseudoplastics examples, interesting example is ketchup, because you can experience this yourself. When you push the ketchup out of the bottle with a greater velocity, it becomes easier. So more ketchup actually flows, right? So paints, blood, yogurt, and mud. Shear thickening materials, the best example is the mixture of cornstarch and water. In these movies, animated GIFs, that you see examples of shear thickening materials that were also mentioned in the introduction, remember, lecture. So in this movie, you see a person who, in the first place, steers slowly the mixture of cornstarch and water, where the steering is slow, therefore the resistance is less, therefore flow is easier, seemingly apparent viscosity is less, but when the person hits the mixture behaves like a solid. So the similar observations are done for the person walking on the mixture of cornstarch and water. So person is just walking. So if you walk fast enough, so you can easily go from one side to the other side of the pool filled with the cornstarch. So without sinking. So the another example here is that the person is, you see, uh, um, deforming the cornstarch water mixture. When the deformation rate is high, it behaves like a semi-solid material, but when the deformation is stopped, then you see it starts to flow. Another interesting example is here where the non-Newtonian shear technique material is put on the speaker, and when the speaker is activated with a song or some frequency of the vibration, you see some creation of some interesting shapes on the surface of the non-Newtonian fluid. So there are many more videos on Newtonian fluids on YouTube if you are interested in just look for it. So besides the pseudoplastic, dilatant, non-Newtonian fluid behavior or Newtonian fluid behavior we observe here, we also have non-Newtonian fluids whose behavior is viscous behavior or flow is activated beyond some stress threshold. So Bingham plastic is the kind of material that is typically observed, this kind of behavior is typically observed in cement paste or mortars, where the viscous flow is inactive up to some stress value, which we can consider as the yield stress threshold. But once the stress has reached this value, then the flow starts and the flow behaves like a Newtonian fluid. So this material is referred to as Bingham plastic, okay, and the behavior is described by Bingham's equation that is given here. So this is a relatively successful model to describe the behavior of highly concentrated materials, semi-solid like materials or fresh concrete, you see. We have also viscoplastic response that you see here. Again, after some threshold responses, like the pseudoplastic material. But in order to activate that flow, you need to overcome this, again, threshold stress. Okay, so viscosity is temperature dependent, that we know, and viscosity decreases. In other words, it becomes easier to flow for a fluid when you elevate the temperature. And this dependency is generally expressed through several models, but the most widely used model is the what we call Arrhenius model. So two versions are given here. Let's concentrate on the one on the right. So where we have the viscosity, we have some coefficient A inverse, or you can call it anything, let's say B, exponential function, what we call the activation energy divided by the thermal energy, where thermal energy is given by the universal gas constant times the absolute temperature. Generally, temperature is expressed in terms of kelvins. Okay, so this expression actually says that as you increase the temperature, due to the inverse proportionality, inverse relationship, viscosity decreases. So that makes sense in when you plot this function with respect to temperature, you see such a decreasing tendency. This is actually a figure taken from a paper that was published in 2009, not so far away. So here you see an experimental data. Okay, the vertical axis is the viscosity in millipascal seconds, and the horizontal axis is the temperature. And the data points that are denoted by field circles refer to the viscosity of honey at different temperatures. All right. So when you look at the Arrhenius fit, that is the dashed line, you see relatively a good fit of the data. So you can use Arrhenius equation to explain temperature dependency of the viscosity. In other words, the higher the temperature, the smaller the viscosity becomes. In other words, resistance of the fluid with temperature decreases against resistance of the fluid against flow decreases with temperature. So besides the temperature, we have also uh, in suspended particles in a fluid, we have effect of the particles on the viscosity of the fluid can be taken into account through such a formula that is given by eta is equal to eta 0 times 1 plus 2.55. So the phi here denotes the concentration of particles, where eta 0 is the viscosity of the parent fluid. Okay, there is also a quadratic version of this equation. And one has to say that one has to note that this linear relationship holds only for dilute solutions, and it would be inappropriate to use this equation for concentrated mixtures, for example, cement paste, fresh concrete. It's good to also know that the first equation is due to Einstein. He published this in 1911, Annalen der Physik. Here in German, that is written that K star is the viscosity coefficient of the suspension, where the phi, in this case var phi, is the concentration of the particles in the fluid. Okay, so when you like to mathematically model the viscosity or viscoelasticity, viscoelastic material response, what you need to do is, in the first place, you need to use rheological models. That is very representative, that is very intuitive, and the key viscoelastic rheological models, or sorry, key rheological models used to model or describe the viscoelastic response are the Hooke element and the Newtonian element. Okay, so Hookean model is nothing but the model for elastic response that is represented by the spring. So elasticity is the phenomenon where we have energy storage. The dashpot is the Newtonian model to describe, in other words, the viscous response. And the dashpot is the model in which we have dissipation, not the energy storage, but the dissipation. All right. So dissipation can be considered in the dashpot that is actually nothing but the piston that is filled with a liquid, viscous liquid, and the friction between the fluid that is flowing between the piston and the cylinder dissipates the energy that you externally supply. Therefore, if you take such a model and subject to the cyclic loading, as we will see in the upcoming lecture, we observe hysteresis, in other words, dissipation. Okay, so let's first take a look at the behavior of these elements individually, and then we will extend these kind of modeling approach towards viscoelasticity. Let's first take a look at the Hooke element. Hooke element is spring. In this case, we just consider a linear spring with the modulus of elasticity denoted by E. Of course, according to the Hooke's law, strain is proportional to stress through the division by the Young's modulus, or vice versa. Stress is proportional to strain through the coefficient of elasticity modulus, or modulus of elasticity. So in this movie, I'm going to show you several movies here, and in each movie we have on the top the rheological model, in this case Hookean model, and here we have the strain time diagram, and underneath we have stress time diagram, and the one we have here lower right part of this block panel, we have this stress versus strain diagram. Okay, so this is a movie where we have Hookean model is subjected to monotonously increasing strain. So strain is prescribed as a function of time, it increases, spring deforms, and stress also increases, and this is the stress versus strain diagram. And of course, slope of this stress versus strain diagram is our modulus of elasticity. So you can make a prediction about that by just looking at this change. So within, you see here, within 1% strain, it increases about 10 megapascals, right? So then you can say that it has one gigapascal uh, 1 gigapascal elasticity modulus. So what happens if you deform the spring hooking element with a constant stress? So what we will see is, in the first place, we will keep the stress 0, and then we will increase it like a Heaviside function. We will introduce a jump and then keep the stress constant and then unload again. Let's see what happens. It is stationary. When the stress jumps to the value of 50 megapascals, spring immediately responds without any delay. That is the typical uh, feature of the spring in this rheological setting, where we don't observe any delay in the response. Response is instantaneous. And then when we keep the stress constant, spring remains stationary. And then when the time is about 180, boom, the spring goes back and we again observe instantaneous response. Both in the loading and unloading parts, you see instantaneous response of the spring to the loading. Again, boom, keeps stationary. No time dependency, in other words, no rate dependency. And then when we unload, it goes back immediately to the undeformed state. So what happens if you subject the when you subject the Hookean model to sinusoidal loading? So strain is prescribed as a function of sine, okay? And you see stress strain curve. Stress essentially follows the strain without any lag, right? Phase lag. Therefore, we don't observe any dissipation, any hysteresis. You are going back and forth on the same curve. This is what we defined as elasticity without any material behavior, without any dissipation. You can do a similar thing with the cyclic loading, like a sawtooth function. Again, on the same story. So these two different loading functions will make a difference when we load the dashboard similarly. Okay, so elasticity is the material response. We don't observe any rate dependency. Elasticity is the material response. We don't observe any, where we don't observe any delay. So response is instantaneous. And elasticity is the material response. We don't observe any dissipation. Loading and unloading curves always on top of each other. In other words, the amount of work you do on the material is perfectly stored inside the material. It's like a perfect energy storage medium. Okay, what happens if you take a dashpot? So this is the Newtonian element. You have a dashpot that is filled with the viscous fluid, whose viscosity is denoted by eta. So then rate of the strain, in other words, the time derivative of the strain, is proportional to stress through the 1 over coefficient of viscosity, reciprocal of the viscosity, or stress is proportional to the rate of the strain, but the coefficient of viscosity. Sigma is equal to eta times epsilon dot in this case. Of course, here we have a uniaxial deformation, but of course, within the piston, we have shear-like deformation, but this is reflected in the overall macroscopic viscosity coefficient in the model. So again, here you see what you see is a symbolic representation of the linear dashpot. So separation of these two vertical lines would represent the evolution of the viscous strain. Again, we have strain versus time, stress versus time, and stress versus strain diagram. In the first movie, we observe the response of the dashpot when it is subjected to monotonously increased strain. You see strain is increased linearly, and the dashpot actually separates, expands, okay, and stress is constant. So that is in contrast with the elasticity. Since the stress is proportional to the rate of the strain, here the slope of this curve is the rate of the strain. This slope times the viscosity will give you the stress. So from which you can actually predict the value of the coefficient of viscosity used for this simulation. And when you draw the stress versus strain, since strain is increasing monotonously, stress is constant, we have a horizontal line. What happens if you subject this to constant strain? Sorry, constant stress. So as you see, at 20 seconds, I increase stress from 0 to 500 megapascals and observe what happens to the strain. So this equation actually says that when stress is constant, rate of the strain is constant. And when the rate of the strain is constant, strain, of course, varies in time linearly, and the slope of this curve is, of course, nothing but something related with the viscosity. Higher the viscosity, smaller the slope is. Let's play this again. Boom. And then stress is constant, and stress divided by eta is the slope of this curve. Stress increases. When we unload, you see, stress is now 0. Stress is 0 means the rate of the strain must be 0. Therefore, dashpot remains where it is. It doesn't move anymore. All right. And in the stress strain diagram, we have in the first place when the strain is 0. Okay, first 20 seconds, your point is here. And then when you increase the stress, you jump to the stress value here. Strain increases linearly. When the unload, strain essentially remains permanently in the dashpot. It, as you see also here. Let's play again. We activate. Dashpot opens. And then when we unload, observe dashpot essentially remains where it was. And this deformation remains as a permanent deformation in this particular model. Okay, so you see the key difference between the elasticity and viscosity. So let's take a look at the response of the dashpot when it is subjected to sinusoidal strain. In other words, we apply here strain, whose variation obeys the sine function, where we have two waves of the sine function. And in contrast to elasticity, we have a phase lag between the strain and the stress. We apply the strain. This is the stress, and you see when the strain is maximum, where the rate of the strain is 0, stress is equal to 0. So we have such a lag, and this lag results in such an interesting stress strain curve. Okay. Let's play it again. You see the response of the dashpot. So when the rate of the strain is maximum, in other words, when the strain is equal to 0, the rate of the strain is maximum, then stress is maximum as well. You see this is like pendulum-like behavior. Okay. All right, so when you do a similar thing with the softwood function cyclic loading, what you obtain is a box-like hysteresis. So you see, boom, boom, again, unload. So you see, when the strain rate is constant, stress is constant. Then here to here, we have a negative slope. Here to here, we have positive slope. At the turning points where the strain rate changes the sign, we have actually a discontinuous stress response because there the derivative is not defined, right? So at the corners of this sawtooth function, rate of the strain is not defined. Therefore, stress jumps. And the stress strain curve has such a purely dissipative response. We don't have any energy storage, but everything is dissipated in the form of such a rectangular hysteresis. So in the upcoming lecture, we will consider the following three fundamental rheological models of viscoelasticity, namely the Maxwell model, the Kelvin model, and their combination, namely the so-called the Burgers model. Okay, so that's it. I like to say about the first part of viscoelasticity. I'm gonna upload these movies as MP4 files that you can play as many times as you like. Uh, and okay, I talk to you later. Bye bye.